So the most common problem on the exam. The most common problem was 2 part B, definitely. Is there any, before I go there, is there anything related to question 1? Other than the computational mistakes which some people did, but.
So 1 was worth 18 points and 2.
1 is 18, yeah, they were distributed like, let me find that thing, yeah, 8, 4, 4, 2 for the first question and 4, 4, 4 for the second question.
Wait, sorry, can you repeat that?
8, 4, 4, 2, 4, 4, 4. Mm-hmm. I can scan the solutions with this, with the top cover if you want.
I guess assuming the final is going to be cumulative as well.
It's going to be cumulative, but it's going to, I would assume because it's a longer exam, it's 1 hour and 50 minutes, the final, it's going to have 3 questions, I would say. If it has 3 questions, 2 of them would be on the new stuff, and just 1 on everything else, and we'll look at some sample exams to see what I mean.
Thanks.
Mm-hmm. All right, so question 2, part B. I'm saying they're using part A, and there is a way to use it actually, it's not just. So if you've done part A correctly, that's where you find the basis and everything. You end up with E1, 1, 0, 1, 1, which is T of E1. Then T squared of E1 was 1, negative 1, 2, 2. Okay. And when you add the third vector, which is T cubed of E1, and that was 0, negative 3, 3, 3, it turned out to be dependent, right? And you know that's where you stop, and this turns into a basis. This set is independent. So T cubed of E1, in the process of checking that this is a basis, you would set it equal, you know, with a linear combination of everything else, and you would solve for the coefficients, and it turns into a 0, 0 times E1 plus negative 3 T of E1 plus 3T squared of E1. Right, so the cube, so the next vector turns out to be a linear combination of the first 3, and this is the linear combination that you get. Okay, so now there was that theorem that helps us find the basis that is telling you to go step by step, right? Take E1, then apply T to it, see if it's independent, put the next one in, and so on. But once you get to a system that, to a set that is dependent, if you move everything to one side, those coefficients are actually giving you the characteristic polynomial of the restriction of T to W. And it was negative 1 to the dimension of W, which is 3, right? We found 3 vectors there. And then, instead of T cubed, you put T, instead of the operator T cubed, you put little t cubed minus 3T squared plus 3T. Then the free coefficient would be 0 there, because it has a 0 coefficient. Okay, so this is the characteristic polynomial of TW. And we actually check that in general, it divides the characteristic polynomial of t, but here it says, and check and verify that it divides the characteristic polynomial of t. And for that, you actually had to find the characteristic polynomial of t. So if you go back to t, T alpha minus T identity, where alpha is the basis for R4, right? Alpha is the standard basis. Alpha is E1, E2, E3, E4. So what's the matrix of T in this basis? You have T in front of you. So if you apply T to 1, 0, 0, 0, so E1, you get 1, 0, 1, 1, right? Express that in the standard basis. That will be your first column. Apply T to E2, 0, 1, 0, 0. You get 1, 1, 0, 0. Apply T to E3, so C is 1, you get 0, negative 1, 1, 0. And apply T to E4, you get 0, 0, 0, 1. Okay, so this is the matrix of T in the standard basis. So the characteristic polynomial of T turns out to be the determinant of this matrix. 1 minus T, 1, 0, 0. 0, 1 minus T, negative 1, 0. 1, 0, 1 minus T, 0, 1, 0, 0, 1 minus T. And if you expand along, let's say, the first row, you get 1 minus T times the determinant of this matrix, and that's upper triangular, so it's just 1 minus T cubed. And then minus, right, this 1 here with a negative sign because it's in position 1, 2. So minus 1 times the determinant of the matrix, 0, negative 1, 0, 1, 1 minus T, 0, 1 minus T. Delete row 1 and column 2 of the original matrix. And that is 0, 0, 0 minus plus 1 minus T. So it turns into this, which is the same as that. Okay, and who is that? Here it is. Except the negative sign that you can factor out, you get the characteristic polynomial of TW. Now, so this was worth 2 points here out of the 4, and this was worth 2 points. That's not the only way to find the characteristic polynomial of the restriction. It's the simplest way, though, the fastest, because you've done all this work in part A, so all you had to do was to copy the coefficients. That was it. You can still find the characteristic polynomial of TW. How? By using the basis in part A. Yeah. So the basis has 3 vectors, right? V1, V2, V3, right? So you do TW of V1. What is that? Well, we know that is V2 because that's what V2 is. So when I start writing it as a matrix in this basis beta, the first column will be 0, 1, 0. Because expressed as a linear combination of V1, V2, V3 has those coefficients, 0, 1, 0. What is TW of V2? TW is just T, right? With the sub W just means I'm restricting to that set. When I apply it to V2, I get V3, right? Because that's what V3 is. 0, 0, 1 is V3 expressed in that basis. And finally, TW of V3 is like T cubed of E1 in the end, which is something that you expressed before as 0 E1 minus 3, right? So 0 V1 minus 3 V2 plus 3 V3. That's the linear combination that you got. So you end up with 0, negative 3, 3. That's the matrix, and then to find the characteristic polynomial, you do the determinant of this matrix minus Ti3, and it will turn into this. And for some reason, I mean, there are people that did this, which is what I had in mind, honestly, but for some reason, most of you went in this direction and got stuck somewhere along the way. But I will post the complete solutions and exactly how the points were distributed. Okay. So let's move on. Are there any other questions about the exam? All right. So we start chapter 6, which is about inner product spaces. So 6.1, inner products and norms. So we're still dealing with vector spaces, but we're adding an additional thing, an additional structure to a vector space, and that is the notion of the inner product. So on a vector space V, an inner product is seen as a function that looks like this. It has two variables, so it's defined on F cross F, right? Both entries, each of the two entries are in F. Oh, sorry, in V. That's not what I meant, in V. So I define on a pair of two vectors with values in the field of scalars, R or C or whatever it is. Okay, so you assign to every ordered pair of vectors a scalar in F. And that scalar is denoted like this, inner product of X and Y. Okay, and you make this assignment with the following properties. You need this map to be linear in the first, right? In the first argument. So if you have x plus z in the first comma y, this is the same as the inner product between x and y plus the inner product between z and y. Also, still maybe linear in the first, it behaves well with respect to scalars. So C is something in F. So you can pull out the scalar from the first entry of the inner product. Now, property 3, or C here, if you want to flip the two entries inside the function, you can do that, but you have to take the complex conjugate in case you're dealing with a field of complex numbers. I mean, you take it anyways, but what happens if they are real, if the field is the field of real numbers? What's the complex conjugate of a number itself? Nothing changes, right? So if you're dealing with real numbers here, flipping position is okay, right? Doesn't change anything. And finally, assumption D, the inner product between any vector and itself is strictly positive, provided that the vector is not the zero vector. Okay, so let's look at some examples. Okay, so the standard example is on a vector space f to the n, which would be r to the n or c to the n. So let's start with, I don't know, with 2 components, c squared. So a vector in c squared, x, looks like this. A1, A2 is a pair. And y is B1, B2, both complex numbers. We define the inner product between x and y to be A1 times B1 conjugate plus A2 times B2 conjugate. Okay, so let's see what happens here. Property A. The inner product between x plus z and y. Z is a third one, so let's say it's C1, C2. Is the inner product between, well, x plus z is A1 plus C1, comma, A2 plus C2. And y is B1, B2. Okay, so I take the first entry of the first vector times the complex conjugate of the first entry of the second vector. So A1 plus C1 B1 bar plus A2 plus C2 B2 bar. But this I can split like this. I can regroup and end up with the inner product between A and B plus the inner product between C and B. Which, of course, that doesn't make sense. I call them X, Y, and Z. X, Y, plus Z1. Okay? So that's the first property. Let's look at the second property. C times the vector x is the vector CA1, CA2. Inner product with the vector B1, B2, according to this definition, will be CA1, B1 bar plus CA2, B2 bar. Factor out the C, and then you end up with the inner product between x and y again. Switching the entries. The inner product between x and y, complex conjugate, is A1 B1 bar plus A2 B2 bar, all complex conjugate. That distributes right over sum over a product of complex numbers, so it turns into A1 conjugate B1 plus A2 conjugate B2. And that is, it's multiplication. I can look at it backwards, right? The inner product between y and x. Okay, what else? Inner product between a vector and itself is always strictly positive if the vector is non-zero. What's the inner product between x and x? Well, it's A1, A1 bar plus A2, A2 bar, right? But what are those? When you have a complex number z and you multiply it by its conjugate, what do you get? The modulus with the magnitude of the number squared. So, like this. So it's the sum of two squares, which is always greater than or equal than 0, but when will it be 0? when both numbers are 0, so the vector is the 0 vector. Now, of course, this was a very specific example on C2, but again, this could be expanded to the entire Fn in the following sense. So example 2. Fn, if X is the n-tuple A1, A2, An, and Y is the n-tuple B1, B2, Bn, define the inner product between X and Y to be the sum I equals 1 to n Ai Bi conjugate. Right, and then everything that we carried, in the previous example would be done here in the same way. So this is actually called the standard inner product on Fn. Okay, and Fn, which was a vector space, if we add to it this inner product defined here, we call it an inner product space. If you have a vector space and you define on it an inner product, you're going to get what is called an inner product space. But it's important to specify the inner product, because on the same vector space, you can define more than one inner product. So if somehow I come up with another inner product, let's call it sub 1, then this would be a different inner product space than the one above. You have to specify, or you have to be given the inner product in order to make sure you understand what's going on here. Okay, on spaces of matrices, there is also this notion that helps with defining very nice inner products and very useful. So let me remind you about this idea, the conjugate transpose. I don't know if you've seen it before, or the adjoint of a matrix. So is denoted by A star. Here is the matrix A star with the property that the ij entry of the adjoint is the ji entry of the original matrix, but also conjugate at the same time. So it's what we call conjugate transpose, so kind of like double. So for example, if A is the matrix this one here, let's say. Right, so you can first, if you want, conjugate every entry. Which turns it into this, but the adjoint is the conjugate and transpose. So then you take the transpose of the matrix of conjugates. And like two operations in one. Now, if A is just a real entry matrix, what's the adjoint? It's just the transpose. Nothing to take the conjugate of. Okay, so back to examples. We've seen two of them, so let's look at example 3. Of inner products is the Frobenius inner product on matrices. N by n. So the inner product between two n-by-n matrices A and B is defined to be the trace of B star A. Trace, remember, is the sum of the diagonal entries of the matrix. Okay, so let's check that this satisfies the requirements for being an inner product. The first one is the thing with being linear. So if I have three matrices, A, B, and C, we need to have this identity. Okay, so the inner product between A plus C and B is in fact the trace of B star times A plus C, which is the trace of B star A plus B star C. Now imagine adding two matrices and taking the trace of the resulting sum. There's just the sum of the diagonal entries, but if you add two matrices, you add what's on the trace of the first one, to what's on the diagonal of the other one. Trace is linear. Trace of B star A plus trace of B star C, and that is, of course, the inner product between A and B plus the inner product between C and B. B was that thing with the scalars, so let's say inner product between Ka and B. K is in F. This is the trace of B star times K times A. Now what is if you multiply an entire matrix by the same scalar K? Yeah, because you multiply every diagonal entry by K. Trace is just the sum of those, so you can factor out the K. It goes out of the trace. So this is K times trace of B star A, but trace of B star A is what we define to be the inner product between A and B. Okay, property 2 is satisfied. Property C. That's the one with switching positions and taking the complex conjugate. So I want to look at the complex conjugate of the inner product between A and B and show that this is the same as the inner product between B and A. All right, so on the left we have the trace of B star A complex conjugate. On the right we have what? The trace of A star B. So, what's the connection between A star B and B star A? Okay, let me ask you a different thing. What do you think happens if I do this? Because you take another transpose and another complex conjugate, so you go back to the original matrix. Okay. What happens if I have two matrices, like A star and B, and I want to take the conjugate of the product? It's going to be what? I want to distribute that. How do I distribute? Because remember, the complex conjugate contains taking a transpose. It's exactly like the property for inverses is. It distributes, but it switches positions. So the complex conjugate of A star B is B star A. So what does that mean for the traces? Because here is A star B. Here is B star A, which is in fact A star B conjugate. Complex, adjoint. When you have a matrix, imagine its trace, right? You take the adjoint. What will happen to its trace through the adjoint? The adjoint takes the transpose, right? The transpose doesn't do anything to the diagonal. I don't care about that, right, for taking the trace. But the adjoint also puts complex conjugates on top of every entry. So when you take the trace of the adjoint, you're going to get what? The complex conjugate of the trace of the matrix. So trace of A star is trace of A, which is a number, right? And then I'm going to take complex conjugate of this. But isn't this exactly what I have here? Trace of A star B is the trace of A star B conjugate, everything, adjoint, everything conjugate. So, yes. And finally, inner product between a matrix and itself should be strictly positive unless the matrix is the zero matrix. So you have a matrix A and you take the trace of A star A. Let's take a quick look at A star A. So the trace is the sum of the diagonal entries, right? So that is the sum of A star A, II. Okay. But the II entry of a matrix is the sum of the first matrix entry Ik times the second matrix entry Ki. Remember that way of expressing an entry of the product in terms of the entries of the two matrices. So this is the sum I equals 1 to n, the sum j equals 1 to n, A star ij, A ji. Okay. What is A star ij? How do you find the ij entry of the adjoint? Is the ji entry, right, of A, and then also complex conjugate. Okay, but what we've got in the end is this. It's right. Every term is a complex number times its conjugate, so it's the magnitude squared, right? So now we got a sum of magnitude squares, which is going to be strictly positive, is 0, of course, if every term is 0. A is the 0 matrix. Okay. So we've seen an example on matrices. Let's see one on functions. So we have that standard inner product on Fn, right? So we know how to deal with that. Now we've seen matrices. On functions, here's one example. V is the vector space of continuous functions defined on 0, 1 with values in R. So on this one, define the following. What will be an inner product? So inner product between f and g is the integral from 0 to 1 f of t times g of t dt. Okay, let's go through the properties of the definition of the inner product. So it has to be linear in the first. So if you replace f by f1 plus f2, does it distribute? It does, because it's just the integral of f1g plus f2g. So it splits into 2. If you multiply f by a scalar k, well, k will go inside the integral, but then it can be moved outside the integral, so it works. If I want to switch positions, what happens between f and g? What's the inner product between g and f? The integral of g of t f of t, but multiplication is commutative, so it is the same as the inner product between g and f, and that is expected because our field is R, right? So there is no complex conjugate here. That's what we need for the third one. Okay, and the inner product between f and f is the integral of f squared, right, which is a positive function. It will turn out to be positive unless f is 0, so it works. Okay, if you want to expand this to an example where you would allow functions to have continuous, to have complex values, you can look at this one. Continuous functions defined on 0 to pi with values in C. Defined by 1 over 2 pi, integral from 0 to 2 pi. This 2 pi here seems to be unimportant, and theoretically it is, until we get to a certain point where, you know, inner products will have to satisfy certain properties, and this example will do it, you know, with 2 pi as it is with 1 over 2 pi. So f of t times g of t conjugate, integral from 0 to 2 pi. So what's going to be different now? So when I check whether it's linear in the first, same story. If you replace f by f1 plus f2, of course, it's going to distribute inside the integral there. If you replace f by k times f, the scalar could be pulled out, so no difference. But the difference will be when you're trying to switch positions between f and g. So when you take the inner product between g and f, it will look like this, right? And if you're trying to get back to the one above, what you have to do is to take another complex conjugate. And you got back to the inner product between f and g. But we'll see more exactly how this works when we get towards the end of this section, and we'll look into a more specific example. All right, so what to keep in mind so far is that on a vector space, you can define this notion of an inner product. Equipped with that, the vector space becomes an inner, what is called an inner product space. Properties of inner products. First property says not only that the inner product is linear in the first, as requested by the definition, but it's linear in the second. Linear without scalars, right? Just with respect to the sum of two vectors. That's what part A says. So we want to look at the inner product between x and y plus z. But I don't know how to deal with the sum in the second entry. I know how to deal with the sum in the first entry, correct? Because I know that I can split it. To switch the two entries, I'm going to take the conjugate. So I'm going to switch them and complex conjugate. But now inside that complex conjugate, I have an inner product that will split into a sum, right? According to the definition. So yx plus zx. Okay, but then the complex conjugate will also distribute. And the complex conjugate of the inner product between y and x is x and y, inner product between x and y, and the other one is the inner product between x and z. And we're done, right? It behaves nicely with addition in the second component. Now, the scalars that you multiply the first entry by just went out of the inner product as they were, right, according to the definition. But if you multiply the second entry by a scalar, it turns out that it goes out as a complex conjugate. Why? Again, I don't know how to deal with a scalar there, so I'll switch it back into the first position through conjugate. Now pull it out according to the definition in the first entry. I'm allowed to do that. But again, everything happens under the complex conjugate. And now I have the complex conjugate of C times the complex conjugate of the inner product between y and x, which is just the inner product between x and 1. Okay, so we pulled out the scalar from the second entry. It went out as C bar. Part C. Inner product between any vector and 0, or 0 and any vector, will always be 0. Well, if I look at this one, I can express it like this. So in the field F, we have this number, which when added to itself, gives you back that number, and the only such number in a field is 0. And so that's the inner product between 0 and the vector x. But to get x and 0, I just have to take the complex conjugate. The complex conjugate of the 0 vector is the 0 vector. Okay. D. The inner product between a vector and itself is 0 if and only if the vector is 0. Well, it's an if and only if, so two directions. Now, of course, that if x is 0, the inner product between 0 and anything, including 0, will be 0, according to part C above. Backwards. Now, in order to prove this, all I need to do is to say, assume to the contrary that x is not 0. Because if I go back to the definition, when x is not 0, the inner product between x and itself is strictly positive. And we're done, right? We reached the contradiction. So there is no way, right? X has to be equal to 0. So let me move all these things down. E. E is actually pretty useful as a method of proof. So if you can show that for two vectors y and z that are fixed or given, the inner product between x and y is the same as the inner product between x and z, but that holds for every vector x, then y equals z. So we need to show that y equals z. And it's pretty straightforward. Move everything to one side, like the left side. How do I rewrite this into a single inner product?
That would be x minus z.
Why would I subtract
Use
z?
property A.
You would use this one, right? Combine maybe with the second one, c equals -1. It's just linear in the second. That's x inner product between x, inner product between x and y minus z. This is 0, and I know that this holds for every x, right? That's my assumption. Okay, if it holds for every x, then I'm going to use one that I like, which is this one. Why do I like this one? Because of property D. Inner product between a vector and itself is 0 only when the vector is the 0 vector. Here is that vector. So the only time when that works is when y and z are equal. Okay. Now the inner product can be used, is used in general, to introduce the notion of a norm on a vector space equipped with an inner product, so an inner product space. So V is an inner product space. We define the norm of a vector to be the square root of the inner product between the vector and itself. We already checked that it's safe to take the square root, right? And it's part of the definition. The square root inner product between x and itself will always be greater than or equal than 0. So it does make sense to take that square root. So for example, let's think about the inner products that we've seen so far. On Fn, with a standard inner product. So the standard inner product, which is what, it was that sum of AI, BI conjugate, where AI and BI are the entries of the n tuple. So the standard inner product will generate a norm, right? The norm of a vector x, an n tuple x, in Fn. What will it be? X being, let's say, A1, A2, AN. Square root of the inner product between x and itself. I said that the standard inner product was the sum of AI, BI conjugate. There is no BI. BI is still AI here. So it's the sum of AI conjugate. Which is the same as that. These complex numbers. And that's something that you might have seen before in Rn as well. In fact, you've seen it. The length of a vector in R2, how do you compute it? Isn't it the square root of the sum of the squares of the sides if you form a right triangle, let's say, right? That's exactly what this is. Same thing, only that it's generalized to Rn and then to any Fn. Matrix is n by n. The Frobenius norm. The Frobenius norm is, of course, the norm that you get out of the Frobenius inner product, the trace of B star A. So if A is an n by n matrix, the Frobenius norm, it's customary to put an F. Now, there are so many norms on matrices that could be used that things will definitely get out of control. So that's why they put indices, and this is an F. This is one of the most important ones. So the Frobenius norm of a matrix is the square root of the Frobenius inner product between the matrix and itself, right? And the Frobenius inner product was the trace of B star A, in this case, A star A. The trace of A star A to the power 1/2, basically. Yeah. Let's look at the properties that the norms have in general. And if you want to make more sense of this, you can think about vectors, right? The length of a vector, if you have a scalar times a vector, you can always pull out the absolute value of the scalar, right, out of the length. You can factor it out. And that's exactly what part A is saying. So let's see. If I want to find the norm of a scalar times a vector, I know that's the square root of the inner product between Cx and Cx, by definition. And now I'm going to start pulling out scalars out of the inner product. This from the first entry goes out as C, right? The other C from the second entry goes out as C conjugate. But this C times C conjugate is the magnitude of C squared, which can be pulled out of the square root. The magnitude of C times the norm of X. Now, the norm for vectors, if you think about it, will measure length, right? In general, it kind of measures distance between objects in your vector space. It has to be positive, right? You cannot measure length with negative numbers. And that's exactly part B is saying, that the norm of any vector is greater than or equal than 0. It's going to be 0 only when you're dealing with a 0 vector. And you get it out of this. So the norm of X, which is the square root of the inner product between X and X, is 0. If and only if the inner product between X and X is 0. And haven't we just proved that this is equivalent to X being 0? In any case, it says here, the norm is greater than or equal than 0. Of course it is, right? It's the square root of a positive number, so it's greater than or equal than 0. Okay. Now, two important tools when dealing with inequalities with any kind of objects, matrices or vectors, will be those two inequalities, the Cauchy-Schwarz and the triangle inequality. So Cauchy-Schwarz, you might have seen that inequality in other forms and other courses. It has all kind of different proofs. Some are nicer, some are very ingenious, some are very strange, and none of them is very natural, I would say. So here is one of them, one of the proofs for Cauchy-Schwarz. It starts by noting that if y is 0, I'm looking at this inequality here. When y is 0, the inequality is automatically satisfied, because on the left you get the inner product between x and 0, which is 0. On the right you get the norm of the vector 0, which is 0. So you get 0 less than or equal than 0. So true. So we can assume that y is not 0. Not the 0 vector. And it starts very unnaturally, let's say, by noting that for every scalar c in F, the norm of x minus cy squared is a number that is greater or equal than 0, which of course it is, right? But now they develop on this. The norm of x minus cy squared is the inner product between x minus cy and itself. Remember, c is anything, at the end is going to be replaced by a very specific thing, which will turn everything that we get into Cauchy-Schwarz. Right? So it's going in this direction, it's kind of blindly going there, but in the end it will give you what you need. Okay, so now you have the inner product between x minus cy and itself. We're going to start distributing and splitting this. So first, using the first entry, I can also pull out that c. So it's x comma x minus cy minus cy comma x minus cy, and I pull the c out. I don't know why I pulled it with a bar, because it's in the first entry, right? Without a bar. All right, second entry. From the first inner product, xx minus xcy. Now c goes out as c bar from the second entry. Then cyx minus cyx plus c bar yy. Let me know if you notice anything strange in what I'm doing. I'm just separating them according to linearity in the first and in the second, and how to pull out scalars from the first and from the second. That's all I'm doing. Okay. And the key part is the following. We're going to use the following value for c. Inner product between xy divided by inner product between yy. Remember the assumption, that's where it comes into play. Y is not 0, so its norm is not 0, so I'm allowed to divide by that inner product between y and y. Okay, let's see what happens when you replace c by this. So 0 less than or equal. Inner product between x and x is just the norm of x squared. What is c bar? Well, it's the bar of the inner product between xy divided by the complex conjugate of yy times the inner product between x and y minus inner product xy over inner product yy times inner product yx plus c bar times inner product between yy. By the way, I'm writing here inner product between y and y complex conjugate. Can I just drop the conjugate? Everything could be over C here, right? But you take a vector and you take the inner product with itself. That thing is...
That's 5-dimensional properties.
Yeah, it's a real number. So when I'm saying it's greater than 0, it automatically means it's real, right? Real and positive, right? No matter if you're dealing with complex numbers to start with, if you take the inner product between a vector and itself, it's going to be a real number. So writing that conjugate or not on top of this denominator, it doesn't make any difference. But anyways, this term and that term cancel out, right? Because one of these goes away, and you end up with the same thing. So 0 less than or equal norm of x squared minus xy, but yx is in fact xy complex conjugate, right? And inner product between y and y is the norm of y squared. Okay. So norm of x squared is greater than or equal the magnitude of this complex number squared. Because on top you have that number times its conjugate. And I think we're done. This is what Cauchy-Schwarz says. Take the square root of both sides, everything is positive. And now, this holds for any inner product and its associated norm and any kind of vectors, right? So this now you can translate into whatever situation you're dealing with. Like for instance, if you're working inside Fn with a standard inner product, and X is an n-tuple, and Y is another n-tuple. How does the Cauchy-Schwarz translate? Magnitude of inner product, the standard inner product is the sum of EI BI conjugate. Less than or equal than, what's the norm of X? Square root of the inner product between X and itself. So sum I equals 1 to n AI conjugate. Norm of Y is the sum I equals 1 to n BI conjugate. And here it is, Cauchy-Schwarz for numbers, for complex numbers. Okay, you can replace AI and BI by whatever complex numbers you want or real. This will be satisfied, this inequality. Let's look into matrices with the Frobenius inner product. What does Cauchy-Schwarz become? Magnitude of the trace of B star A, X is A and Y is B. The magnitude of the trace of B star A is less than or equal than trace of A star A to the 1/2 and the square root of trace of B star B. Okay, so you can translate it into different things depending on the vector space you're working on and the actual inner product that you're using on that vector space. Okay, so we're not done with this. We were done with Cauchy-Schwarz, so we have one more. Triangle inequality. You've seen this before, right? Geometry. The length of one of the sides of a triangle is less than or equal than the sum of the lengths of the other two sides. That's hence the name triangle inequality, right? But it holds for any vectors, any vector space. So x and y. We need the magnitude of x plus y, the norm of x plus y being less than the norm of x plus the norm of y. So that was part B. It's more straightforward. So we're going to show that the norm of x plus y squared is less than or equal than the norm of x plus the norm of y, everything squared. If we show this, we're done, right? We just take the square roots of both sides, and we get what we need. So let's start with the left side. And usually when you're dealing with identities or inequalities with norms, it's good to somehow come up with squares, right? Because the square of a norm is the inner product between the vector and itself, and it's easier to work with. The norm of x plus y squared is the inner product between x plus y and x plus y. And now if you spread everything out according to linearity, what do you get? Xx, xy, yx, and yy. Okay, and that is the norm of x squared plus the norm of y squared, the last term, right? Plus those things in the middle that we have to deal with. The second term is, in fact, the complex conjugate of the first, right, in that group. Remember the notation, if you have a complex number z and you add its conjugate to it, what do you get? Z plus z bar is twice the real part. 2 times real of x1, right? So twice the real part of x1. Okay, so what do I need? I need to show that this is less than or equal than this guy here, right? And that is the norm of x squared plus the norm of y squared plus 2 times the norm of x times the norm of y. That's what I want, right? That means we want to show that the real part of this thing is less than or equal than the product between the norms of x and y. Okay, but the product of the norms between x and y is something that came up in Cauchy-Schwarz, which was the previous part. This is what we know from Cauchy-Schwarz. So then, is it true that the real is even smaller than this? Because if that's true, then we're done. Make sense? Okay. And I'm not going to make it about any inner product and about any vector v. I'm just going to make it about a complex number z. So you have z equal to a plus bi. The real of z is a, right? What is this? The magnitude of z. Square it. So is it true that the real part, which we called a, is always less than or equal than this? Of course it is, right? So for this, using it for that complex number, we are done. Okay. Let's just look at an example. There is one more idea in this section that kind of connects to the next one, but I don't have time to do that. So let's just look at an example. This is exercise 19, part B. Show that the absolute value of the norm of x minus the norm of y is less than or equal than the norm of x minus y for any two vectors x and y in a V, which is an inner product space. So it helps to think about numbers. When is the absolute value of a number less than 5, let's say? When the number is between -5 and 5. So what's inside the absolute value would have to be between norm of x minus y and negative norm of x minus y. So if we can show this, we're done. So there are two inequalities that we need. Let's look at the first one. I'm going to rearrange everything so I don't see any negatives. Why is that? Because I'm thinking about the triangle inequality. So I'll move things around. 1 turns out to be equivalent to showing that the norm of y is less than or equal than the norm of x plus the norm of x minus y. Does this one look like the triangle inequality? Maybe not yet, but for which vectors? Now it does. Isn't this the same as the norm of y? Y is, well, I'm trying to make it look exactly as the right side, that's why I'm kind of forcing it here. But y is x if I do x minus y minus x, it turns into negative y. But the norm of negative y, you know how you can pull out the scalars from inside? They go out in absolute values. So the norm of y and the norm of negative y are one and the same, right? It doesn't matter. But now expressed as a sum, using the triangle inequality, it turns into the norm of x minus y plus the norm of negative x, which again, that's the same as the norm of x. What is 2 equivalent? Norm of x less than or equal than the norm of x minus y plus the norm of y. That's even more straightforward because x is in fact x minus y plus y. So it's the sum of the 2 vectors on the right, which again from the triangle inequality, less than or equal to the norm of x minus y plus the norm of y. Okay. All right, so we're done with all those properties. There is just one more idea, which I'm going to take it out of here into the next lecture, is the notion of orthonormal and orthogonal vectors. We'll just look into some examples and then connect that to the next section, which will be the Gram-Schmidt orthogonalization process, a very not nice and messy process, but doable, so we'll look into that next time. Stop here.